In today's video, I'm going to be going through the third episode of the organic chemistry series that I'm doing. If you haven't watched the other two previous episodes, then I recommend doing that to get a gauge of what exactly organic chemistry is and some things about the alkanes if you're completely new to this subject matter. But if you're not and you have been watching through or you know a bit of previous knowledge, then come on with me. Today I'm talking about the reactions of alkanes, and despite, as you see here, alkanes being relatively inert, due to the high strength and solidity of the C and CH bonds. As you'll see in this image here, it's only containing CC and CH bonds, and these bonds are quite solid, quite strong, and it only contains these bonds. It's a saturated hydrocarbon. Ignore these little things here that look like wedge shapes. That's just to show that it's a 3D shape rather than in the 2D plane, but we're not worried about that at all now. Now, the two major reactions that alkenes are involved in both involve free radicals. These are things that have unpaired electrons and are unpredictable and dangerous. If I try to draw a free radical, say it's like a chlorine free radical, a chlorine ion would have Cl, then it would have dot, 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 dot. That's a chlorine ion, and then it's all going to disappear. And a chlorine atom, which would be a free radical, would be Cl dot, 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 dot. It has this unpaired electron which really wants to be paired, and so will go at great lengths to actually get that electron paired, and that can cause some vigorous reactions and actually make the alkenes react in some way. The first reaction that alkenes are involved in is known as cracking, and this is more of an industrial process rather than a reaction. This is where a large alkane is cracked, so to speak, from a larger alkane, like something like this, to form a smaller alkane and also an alkene. So as you'll see, an alkane, through this industrial process, can actually form an alkene. There are many different, I think there's just two different types of cracking. One is catalytic cracking, which involves lower temperatures and pressures than thermal cracking. However, it requires a zeolite catalyst. A zeolite catalyst, if I'm to explain it in simple terms, is made up of, I think, silicon dioxide and aluminium oxide. If you have a look at like a periodic table online, you'll see where those two things are in the table, and you'll be able to maybe deduce their structures and stuff like that, and you'll go onto the internet, search them up, you may be able to see how that actually works. But that's how catalytic cracking works. And then thermal cracking is a thermal way of cracking things and uses temperatures excess of 700 Kelvin. That's how much energy these alkanes need to actually crack and form these free radical alkyls that you see here. Now, the way that this splitting of a molecule is represented is through curly arrows which show the transfer of electrons, and this is known as an organic mechanism. So if I'm to do this here, it's going to be a little bit difficult because it's small and the pen disappears after like 5 seconds. But you go from the center-ish of the bond and you show like that will go like that. It's like a half-headed arrow because that's one electron, and then the other half will go like this. I probably should make the pen a lot thinner realistically, but that's fine. You can see that's how that works. It will split. There's two electrons in this bond. One will go to this carbon, one will go to this carbon, and then you see that here. That's sort of logical. And then to go from these two things to these two is a little bit more complicated. Firstly, either one free radical is going to attack a hydrogen. So we'll say that attacks that, and that then is going to cause this hydrogen to split in the same way you saw before. So that's going to do that. That's a little half-headed arrow. That carbon has already attacked that hydrogen. That hydrogen has an electron in its outer shell because one of the electrons in this bond here has gone to that hydrogen. Then that hydrogen is going to go here and bond with this carbon to form a bond that's got two electrons in it, just like that. And then because this carbon now has two free radicals, two unpaired electrons make a pair, and so that's then going to form a bond with the other carbon atom inside of the structure. And one of these hydrogens here on this outer carbon will transfer to this carbon here, because otherwise this carbon here will have too many bonds. If it had an extra hydrogen, as you see here, in this image it has two hydrogens and an R group. In this image it has one hydrogen and an R group. If it had an extra hydrogen, it has too many electrons for its like electronic structure to be stable, so that's not going to work. and so this hydrogen is going to transfer to here to form an alkene. And that's the first mechanism, I suppose, of alkanes. It requires a high temperatures and highly reactive free radicals to actually get going. The second reaction is known as free radical substitution, and this is actually a relatively useful reaction. I mean, as it says here at the bottom, the reaction itself has a drawback, which I'm going to explain in a little bit, but it's probably the more interesting reaction of the two, and it has plenty of different kind of mechanisms and stuff like that. This free radical substitution reaction involves the heterolytic bond breaking, and that's the heterolytic bond breaking that I mentioned here. That is where two electrons in a bond go like that, and there's a bond here. Each electron goes to one end of an atom to form two free radicals. That's how heterolytic bond breaking works. And it starts with the heterolytic bond breaking of a halogen molecule. A halogen molecule, halogens are often found in sort of pairs. So a chlorine molecule would be found like this. It has a bond between two chlorines, and as you would see in the image before, that would heterolytically split to form two chlorine radicals, and that will be shown on the next slide. Interesting thing about these bonds is that UV light is what's needed to break this bond to start the reaction to form the free radicals, which will then go and attack the alkanes when they're put together in the same environment. And that's why I have this nice little image of the sun here. Now, there are three stages to the whole free radical substitution reaction, known as initiation, propagation, and termination. And the fact that this reaction has a propagation and it kind of goes on and on and on is the reason this reaction has quite a severe drawback. Now, I've already talked about the initiation a little bit, and this is this basically. It's a chlorine molecule, for instance, say exactly the reaction between chlorine and methane. The initiation is to do with the chlorine, not the methane, and a chlorine molecule will form two chlorine free radicals. One of these chlorine free radicals is going to attack this methane molecule, and then this methane molecule is going to go like this. If I can, oh, there we go, pen got. It's going to split heterolytically, so one electron goes to the carbon to form a free radical, one electron goes to the hydrogen to bond to the chlorine, and that will form HCl. This is hydrochloric acid. And then, as you see here, you're left with this methyl radical that has an unpaired electron, essentially. Now, that methyl radical is then going to react with an sort of broken chlorine molecule, because the UV light might not break every single chlorine bond initially, so it's all just completely radicals, and these radicals might also connect back into the chlorine, so this could be considered a reversible reaction, for instance. And this is a radical, so it's reactive, it's going to attack whatever it can find to pair its electron, and what's going to happen is this chlorine is then going to heterolytically bond break, as we saw earlier. This chlorine is then going to bond here and get that unpaired electron, and then you're going to have a chlorine attached to the carbon to form chloromethane, which is a halogenoalkane. And I'm going to talk about the halogenoalkanes as a functional group in the next video, I guess. And as I say, ignore these little wedges here. These are just to represent that the molecule has a 3D structure rather than just being 2D. And this still forms a chlorine radical because this chlorine went to this molecule, and this chlorine's then still left with an unpaired electron. So you start with a chlorine radical and you can end with a chlorine radical. And so an example of the termination of a part, I suppose, of the free radical substitution reaction is two methyl radicals combining to form an ethane molecule. You see, each free radical has one unpaired electron on its carbon, and that can then just form this ethane molecule, just like so. The main problem with this reaction, however, is that it can go on and on and on and on. Because of the propagation, where you start with a Cl radical and you end with a chlorine radical, this chlorine radical, for instance, could then react with this chloromethane, and that could cause one of these bonds to break, another CH bond to break, and then you're going to get a chloromethyl radical and HCl, and then another chlorine's going to come along, donate its chlorine, so now you've got dichloromethane and a chlorine radical, and that could then become trichloromethane, tetrachloromethane, and then you could also have like tetrachloroethane when the termination happens, and you've got like three things. So the main problem with this reaction is that you can get a wide range of halogenoalkanes, and that may not necessarily be what you want. You may just want tetrachloromethane, or you may just want dichloromethane. Chances are you're probably not going to get that because of the reactivity of these free radicals and how unpredictable this reaction can be. I'm sure there are ways, and I'm pretty sure there are ways to try to optimize the yield of certain products by altering reaction conditions with temperature and stuff like that. But I doubt that there's any real set way to just get 100% of one product. Now, to conclude this video, I know this diagram seems a little bit small for now, but as we go through the whole organic chemistry series, it's going to build up and up and up. These alkenes will be able to produce things. These halogenoalkanes will be able to produce things. But alkanes, being a relatively inert homologous series, can produce alkenes, which is another functional group in homologous series, and halogenoalkanes, which is also another functional group and homologous series. And these two have individual chemical and physical properties which differ them from alkanes, which is why they are functional groups, which is why the little special things about them are the functional groups. And as I go through the next videos of reactions of halogenoalkanes and alkenes, you'll see how this can build up and up and up, and you get like a whole massive chemical synthesis pathway which you can just start from. You can go from alkanes to alkenes to all this other stuff, and there are many other ways to produce halogenoalkanes in a far efficient way. If I just I guess spoil this for you now, I suppose you can go from alkanes to an alkene and then to a halogenoalkane through a different mechanism that I'm going to talk about in a separate video, but that will produce a much better yield of a halogenoalkane that you specifically want compared to the alkane and the unpredictable free radical substitution reaction. But yeah, that's about all for this video, and I recommend subscribing for further episodes in the series, and have a nice day.